So officially welcome everyone to the Developer Basecamp organized by the Starknet Foundation. This is actually our 13th edition, but we're not going to confuse everyone with the number. Let me change my slide. Can you see my slide changing?
Yes.
Perfect. So this is our team. So my name is Sitong. I'm from Taiwan, but I'm now based in Barcelona in Spain. I'm working on the ecosystem team at the Starknet Foundation with David. And I mainly work on different programs, different Basecamps. So apart from this Developer Basecamp, we have another Founder Basecamp on Tuesdays. And I also help with like other initiatives like Hackathons and Startup House. So now pass on to David, who will be our teacher for this cohort. So you will see him every week. He will speaks more than I do. So David, do you want to present yourself a bit?
Yeah, sure. I'm David Barreto. David Barreto. I'm from the Starknet Foundation. I'm a developer advocate, so I work with Suto on the same ecosystem team. My focus has always been on the area of education. I love to create content, to teach, to do workshops, tutorials, to write. So Basecamp is something that is very dear to me that I've been working on for years now, I think at least 2 years. So what you're gonna see in this course is gonna be the culmination of many iterations of the same content. So yeah, happy to meet you all.
Thank you, David. And here we also have Truth, who is actually a graduate of honors from our previous Basecamp in April and May. And now he's our teaching assistant. Welcome, Truth. Do you want to say something to the students?
Yeah, good evening, GM, everybody. So my name is Truth. I'm from Nigeria. I'm graduated from Basecamp 12. That was like my first intro into the Starknet ecosystem and everything. So currently I've been active and doing open source contribution and building a lot of projects in Starknet. I'm an only Dust fellow right now. Welcome, everybody.
Thank you, Truth. So we will be the main 3 people helping you throughout this 6 weeks. So let's go into Basecamp. So Developer Basecamp is a Starknet Foundation initiatives, and the goal is to onboard developers into the Starknet ecosystem. And this cohort, we have 6 weeks. And session 1 is today, is on August 7th. It's actually an optional course. This is actually, I think, the first time we did this class, right? Because what we are trying to do is we realize that there are lots of Web2 developers coming into Web3. So we planned this course to help people that are transitioning from Web2 to gain more knowledge on like blockchain fundamentals. But if you are already a Web3 developers and you know about Bitcoin, Starknet, Ethereum, but you would like to review your content, you are very welcome to stay.
This session came from feedback of Basecamp 12 from the students. They say, oh, we need a dedicated session about Intro to Blockchain, so we created this one. So just comes to say that your feedback at the end of each session is super important because it allows to improve the content even further.
Perfect. Yes. So welcome to stay. And then later on, like throughout this program, we want this Basecamp to be interactive. So it's just not like you sit there listening. We would like you to like tell us what you think, what's your feedback, what's your questions. If you have any questions throughout the class, just feel free to drop it in the QA box below in the function bar on Zoom. So then we will be able to answer you. And then we will have quiz and homework. I will present more in the further slides, so don't worry. And then now, the important thing is if you haven't joined, please join the Discord server. And then there's a Basecamp channel on Discord. You will be able to connect with other students there. If you have any questions, you can ask there. And then Truth, David, and me, we will all like reply to you if you have any questions. And we also have a YouTube channel. So we posted our previous Basecamp videos, Founder Basecamp, Developer Basecamp. We have highlight videos of our IRL events. We have some webinar recordings. So there are lots of resources that you can learn about Starknet in Cairo on our YouTube channel as well. An important thing, you can check out the resource page. This is like the go-to place that you can have with all the resources you need for this cohort. So you can find the recordings there. You can find the presentation slides there. You can find the dates and times of each topics. We can find the links. There's a lot of things happening there. I think there are people asking about links right now. So let me quickly drop it. Oh, Truth dropped it already. Thank you. Perfect. So let's move on. So I want to emphasize that the Developer Basecamp is actually just the first step of your Starknet journey. So Basecamp session starts today, August 7th, and it will end in September 11th. It doesn't mean that your Starknet journey ends right here. And then Later on, in September 15 to October 15, we will have an online hackathon. And this is also an official hackathon organized by the Starknet Foundation. This will be online, so you can basically participate in any corner of the world. And you can like try out the things you learn during Basecamp, try out new idea, try out new project, and then compete for prizes with people around the world. And then later on, what we realize as well is like many developers are interested in participating in projects, in hackathons, but they don't have a project idea yet. So what we are thinking now is that we have a founder Basecamp. So we will matchmaking founders from founder Basecamp who don't have a team yet with people like you who have technical skills but don't have a project idea. So we'll matchmake you together and you can form a team and you can try out new ideas in a hackathon. And later on, I will provide more feedbacks in the coming weeks. And later on, in November 12 to 16, we will have a startup house. And this is a little bit more demanding than a hackathon. You will need to have an MVP to join the startup house. And the goal is that you just go there 5 days, super intense building and learning. And then the goal is to help you to move your MVP into sustainable startups. And this will happen in Buenos Aires in Argentina in November, right before DevConnect. So this is just like 3 big events that were happening in 2025. So as I mentioned, this is just the beginning. So right now we are right here in Basecamp. And later on, after graduating, you can start connect to people like what Truth mentioned. He has been contributing to open source projects. You can do that on the Only Dust platform. We have ambassadors around the world. We have meetups. We have events happening all the time. So you can meet up and meet people around the world with different skills. You can connect and then you won't feel that alone on your learning journey. And later on, as I mentioned, we have hackathons, we have startup houses. And even later on, when your project is more mature, you can participate, for example, apply for seed grants or other mentorship that Starknet Foundation provides. So what I want to emphasize right now is like we were just at the beginning and there are lots of exciting things happening. So be prepared. But now just go back and focus on the Basecamp now, because that's the most important thing right now. So as I mentioned, we have 6 sessions for this cohort. And right now we are right here in the first one. And this is just a bonus session. So like the quiz and attendance will not be taken into consideration for the graduation for this cohort. But then later on from session 2 to session 6, it will be a required session. We will dive into like blockchain fundamentals today. We will present, David will present Bitcoin, Ethereum. Later on, we'll talk about Starknet. We will present Cairo, which is the programming language of Starknet. We will start to write smart contracts. We will do testing. And at the end, we will build a front end for session 4 and session 5's code. So you will have a full stack app after this cohort. So try not to miss any session. If you really miss it, please watch the recordings because it's kind of continuous. So let me present a scoring system. So in Basecamp, we have 60 points maximums that you can get. And we have 3 categories to get the points. So the first one is the quizzes, as I mentioned. So after each session at the end, we will have a quiz. It will be a 4 questions quiz. So 5 sessions from 2 to 6, and then 4 questions. So in total, it's 20 questions. So if you get 1 question correctly, you get 1 point. So maximums, you can get 20 points. And then we have a homework for this program, but it's actually like a homework throughout the program. There's no weekly assignments and things like that. So the homework is also super easy. What you need to do is just follow the live coding like David did in the class. You just follow him, write exactly the same code, and then at the end of the program, publish the code to GitHub, like in a repo link, and that's it. So like there won't be a repo link that we send it to you because we want you to code along with David. There will be recording, as I mentioned. So if you cannot catch up during class, you can watch the recording and code later. So no problem at all. That's also easy. So that's 20 points. That's super easy to get. And then you can also get another extra 20 points by complete Start Links. So Start Link is like an interactive gamified kind of platform to help you learn Cairo. So there are different challenges, like coding challenges, and you solve it by coding, and then you can complete the challenge. So after you complete all the challenge, you get another 20 points. So that's easy as well. So the graduation criteria, if you don't want to do homework, you don't want to do Start Links, you just want to listen to David, then if you complete 25% of the live classes, you can be considered an attendee. If you want to be a graduate though, you need to attend at least 50% of the classes, and then you score 30 points. So in total, there's 60 points, and you get 30 points, you are a graduate. But if you want to be graduate with honors like Truth, then you need to get 48 points. So it's 60 points, you get 48, you are graduate with honors. And at the end of the program, we will give like a spot, which is StarkNet proof of kudos. It's like a POAP, like an NFT on StarkNet to prove that you achieved this program. Okay, so last slide before I give it to David. If you have any questions throughout this program, please drop it in the QA box because it will be in order, so we won't miss it. If you drop it in the chat, we might miss it. And then after, like not during the class, if you have any technical questions that you face anything regarding coding or anything, you can share your questions in the Basecamp channel on Discord. We will reply to you as soon as we can. And for other general questions like how do I do the assignments, where is my points, things like that, you can also drop it in Discord. I will reply to you. Or if you have more personal questions you don't want to share, you can email me as well. And the last thing to remind, check out the resource page because there's also common Q&A. There are lots of links there. So make sure to check the resource page before you ask any questions. And last reminder, be aware of scams in Discord. There's a lot of people trying to be our team, reaching out to people, sending weird links. So if you ask questions and then make sure that the person that reply to you have a badge of the StarkNet Foundation badge. So to make sure that it's us that are replying. Stay safe in crypto. That's it from me. Thank you, David. I'm going to pass it on to you. I take 15 minutes from you.
Thank you. Just to mention about Discord, yes, Sutun, you and I and the mods, we have a badge. Truth doesn't have one, so I'm just going to jump in and identify, hey, this is Truth Discord username, so you know it's him as a teacher assistant as well. Okay, so let me share my screen. I share the slides with all of you if you want to follow with me. Give me a second to set up here, share the screen. And step 2. Okay, I assume you can see the slides now.
Yes.
And yeah, so this is the session 1. This is an optional session for people, mostly who want to learn like the basis of blockchain, Bitcoin and Ethereum in particular. Before we jump into how StarkNet actually works and more details about Cairo, for example. So give me 1 second. Just want to make sure that I have the chat and the Q&A visible at all times. All right. So we're going to start with the OG Bitcoin. So maybe you recognize this newspaper on the right from the Times, dated January 3rd, 2009. And the main title of the newspaper is Chancellor on the brink of second bailout for banks, a reference for the financial crisis and the bailouts that happened after. So this is actually the genesis of Bitcoin. So on that particular date, the date you see this newspaper, January 3rd, 2009, the first Bitcoin block was mined. So that block actually included the headline of the newspaper, right? But you see it right there. The Times, January 3rd, 2009, Chancellor on the brink of second bailout for banks. You can actually go to a block explorer and you will inspect the very first block of Bitcoin and you'll see this message. And this block, being the first one, has a special name. It's called the Genesis block. We can actually inspect it. This is block 0, if I remember correctly. If we go to technical info, there you have Coinbase data. And this is the message that Satoshi put in the first block on the Bitcoin network. So the creator was someone called Satoshi Nakamoto, which we assume is just a pseudonymous. There's no person named like that. Satoshi actually disappeared April 23rd, 2011. That's the last time we heard anything coming from him or from her or from the group. We don't know. After that point, it was the community taking over the maintenance and the upgrades to the Bitcoin as well. Now, to this day, the wallets that we associate with Satoshi actually controls about 22,000 Bitcoin, which is worth about 70 billion. So that is an incredible exercise of self-control that for so long he has not touched any of his Bitcoin at all. Now, let's talk about Satoshi, right? So we don't know exactly who this person is. That's why the image to the right. But what we know is that in 2008, in October, he published what's being the Bitcoin white paper, right? Explaining all the fundamentals of Bitcoin itself. The title of the white paper is Bitcoin, a peer-to-peer electronic cash system. You can see the white paper here. You click the link. You can read it. It's not very long, only 9 pages, so mostly explain at a high level how the system works. So actually, it's a good read. Back to the slides. So it annoys me that when I come back, the menu is still showing. Okay. So at the very first time when he launched this system, the way that he actually launched it, and the community actually knew about it, is because there was an email list that he actually published. Say, hey, this is the white paper. I've been working on this for a while. This is before social media, right? 2008. I think Facebook was just getting started at that point. Then he actually moved to be very active on a Bitcoin forum, which you can go click the link and you will see all the messages that we have from Satoshi from that era. And he was a very active contributor to the code until December 2010. That also comes to show that the first system that Satoshi created for Bitcoin was not perfect. It had some bugs, it had some limitations. So with help with the community, new patches started coming in and the system was made more robust and more efficient over time. The last known message that we have, that we know from Satoshi from April 23rd, 2011, is basically, I moved on to other things. It's in good hands with Gavin and everyone. Right? From that point on, we haven't heard about Satoshi ever since. And of course, his real identity remains a mystery. There's a lot of conjecture about who this person is, but really, we don't know. And the only way to really prove that you're Satoshi is to basically sign a message with the same private key that he was using to mine his own Bitcoin. And no one has able to do that. So what is Bitcoin trying to solve? And by extension, what is Satoshi trying to solve? And one phrase is currency debasement. So what is this? Currency debasement is the loss of purchasing power of a currency, right? The fact that if you have $100 today, you can buy certain stuff. But if you take the same $100, maybe 50 years in the past, you can probably buy even more things with the same amount of money, right? That this is part of the currency debasement. And currency debasement is created by excessive money printing, right? Because printing or money in the fiat system is created out of thin air, right? So more money enters in circulation, and the central bank is the one responsible for creating more money injecting into the system. Now, some of the effects of the currency debasement that Bitcoin is trying to solve is that you enter in this unaffordability crisis for housing, because housing now start to increase in value, not because house became suddenly more valuable, it's simply because the value of the money used to purchase the house is losing purchasing power. You can see the stock market entering in bubble territory or just growing. And this was like evident during the COVID crisis, right? Like the economies was shutting down, no one was going to work, no one was producing anything, and the stock market was still going up after crashing, of course, but still going up while the economy was shutting down. That's because currency debasement. And the most well-known effect is probably inflation, right? Which is the increase of goods and the cost of goods and services, like your groceries, your rent, stuff like that. So to see the effect of this money printing or this currency debasement, you can see at a thing called the M2 money supply, right? There's different ways to measure how much money there is in circulation, in this case in the US economy being the biggest one in the world. And you can see that in 2008, when the white paper was launched, the amount of money in circulation, if you consider M2 to be this, was $8.3 trillion. And by 2025 is $28.8 trillion. In this very steep curve, you can see this is the time of COVID, where the money printing went into overdrive. So you can see that in the span of less than 20 years, the supply of money or US currency in the economy increased by 162%, or just increased by $13.5 trillion in under 20 years. This, of course, is causing all the issues that we discussed before. This is the reason why Bitcoin as well was created, to create some hard money again in the system. So to understand how Bitcoin tries to solve this or create this hardness of money, trying to avoid the same pitfalls of this current system creates, let's talk about the monetary policy of Bitcoin. So in Bitcoin, every 10 minutes approximately, a fixed amount of Bitcoin is created, right? Sometimes I use the term BTC or Bitcoin interchangeably. I use BTC to refer to recurrency, and usually I refer Bitcoin to refer to the network. So this new BTC is a reward for Bitcoin miners, right? So they get every new Bitcoin created or any BTC created goes to miners first. This is known as the network subsidy, and it's a subsidy for the security of the network. We're going to talk more about that later, but for now, just keep in mind the term subsidy because it's going to be important talking about the long-term health of Bitcoin, which is one of the things that Starling is trying to solve as well, right? How do we make this subsidy not rely too much on it for the security of the network? Now, the current reward level for mining a new Bitcoin or a new block, is 3.125 BTC. That's how you get for mining a new block. This amount is cut in half every 4 years. This event is called the halving. Now, the next halving will occur roughly April 2028. The date is not exact because it depends on a block number, but we still are some 3 years far away from this, or 2.5 years. And eventually, the maximum supply of Bitcoin through this process of mining new Bitcoin, but the halving decreasing every 4 years, is going to be 21 million, right? Right now, we are close to, I think, like a 19 or 18 million Bitcoin circulation. So the majority has been mined already. So there's a small portion that is yet to be mined in the future. So we can now put into context, for example, the blue line is the subsidy. So this blue line corresponds with the axis here, which is a little counterproductive, but yeah. It means that at the very beginning when Bitcoin was created, the reward for mining a new block was close to 50 BTC that you will get. And then 4 years later, it half, right? It became 25. And then 4 years later, it became half 12.5 and so forth, right? So we are somewhere along here, 2025, so it's 3.125, as I mentioned before. The white line is the amount of total Bitcoin in circulation, right? All the Bitcoin has been mined so far. And you can see that at the beginning, this curve was increasing rapidly, right? Because the subsidy was very high, which means that if you think about debasement, there was high level of debasement at the beginning of Bitcoin, right? Because a lot of Bitcoin was created in a short time. But as time goes by, the amount of new Bitcoin circulation actually starts to decrease to the point that we assume that at some point it's going to feel almost like flat. Like a new, very small amount of Bitcoin will be created over time, but so small that it's not going to affect the overall circulation. Meaning that as time goes by, the debasement of Bitcoin is going to decrease so much that it's going to become pretty much fixed, right? Which you don't have this property on any type of currency in the world. Not in the US dollar, not in the euro, not even in gold, right? Because in gold, when you find a new mine, or let's say we finally do mining of asteroids in the space, the amount of circulation will increase again. But with Bitcoin through code, it's just going to get fixed to 21 millions at some point in the future. Right now, we are, if I see here, like, 19, or actually seems to be past 20 million at this point. We can compare these two curves. This is the green line is the circulation of Bitcoin over time, and the blue line is the one that the M2 money supply, basically the US dollar in circulation. You can see how they behave very differently, right? At the beginning, Bitcoin was going much faster, fiat was going slower, but then they start to converge. But eventually, as I mentioned, this convergence of the green line of Bitcoin is going to tap at 21 millions, but there's no limit of how much money you can print in US dollar. This could very easily go and bump again the same way that it did here. Now, the way that in the fiat system that we call like any currency, the US dollar, the euro, the yen, this scarcity of the currency is enforced by law, right? It is enforced in the way that there's only one entity that is allowed to print or create new money in the economy. In this case, it's the central bank of each country. So they say like the head of central bank, this is the picture of Jerome Powell. He said, okay, let's print $1 trillion. And that's fine. That's how the economy works, right? But if you try to print your own money, even a small amount, like you're gonna get in trouble, right? This is counterfeit. So the reason that this scarcity is enforced just because the police will prevent anyone from trying to print their own money, right? So there's only one entity that controls this. Obviously, so this type of money, this currency, we call it fiat money. And fiat comes from Latin of let it be done. It's almost like money by decree. And the scarcity is enforced by law or by extension by the threat of violence. Like if you counterfeit money, you're going to get in trouble. So at the end of the day, it's just essentially the threat of violence that keeps the system chugging along. Now, if you think about how Bitcoin enforces scarcity, it's different. It uses actually code to enforce this scarcity, not law and not the threat of violence. And the way it works at a very high level is that, every time you mine a new block, in this case, for example, you solve the challenge of the proof of work, that I'm going to talk more about later, you get rewarded 3.125 BTC right now, okay? And every 10 minutes, roughly, a new block is mined, so someone else is getting the same reward, 3.125. Now, it could happen that someone is going to try to break the rules, right? Like someone say, oh, you know what, I'm going to create like a fake Bitcoin system that is going to allow me to mine every minute, and the reward is going to be 100 BTC instead of 3.125. But what happens is that every operation, every block created in the system is actually verified by the other nodes in the network that are managed by independent operators. So they can very easily detect that someone is trying to cheat by breaking the rules. And when that happens, they basically ignore the block created by this entity, which means that this Bitcoin that they create has no value. It exists in its own universe that is not connecting at all to Bitcoin. So this is roughly how the system is kept in check and how this scarcity is enforced by code. Okay, so we talk about that people mine blocks and they solve a challenge to mine it, but what is the challenge they're solving? Well, the challenge they're solving is called proof of work. You may have heard about that, but let me again explain at a very high level how it works. Later on, we're going to revisit this concept and go a little bit deeper into it. So the proof of work, you have basically two entities. You have the Bitcoin protocol, in this case is the code, Bitcoin, and then you have the Bitcoin miner, right? The person trying to mine a block to get a profit. So what's happening is that the protocol is basically going to say, hey, I'm thinking of a number between 0 and some gigantic number. I can't even pronounce this number. It's gigantic. So the miner, what it does is basically start to guess. Okay, well, is it 5? And the protocol will say, no, try again. He goes, well, is it 32? No. And this game is going to continue billions of times, maybe billions of times, until eventually the miner is going to guess the right number. You say, yes, finally, you get it. That's the right number I was thinking of. Here's your reward, 3.125 BTC. This is new BTC created in the network and given to the miner. And the miner say, okay, great. That's some profit for me. This is a very simplified way to think about proof of work, but it's essentially a guessing game. You have to guess a number, and only the protocol knows the right number. Now, the actual number, like if you go from 0 to a certain number, the actual length of the number changes over time. This is called the difficulty adjustment. Let me tell you why. Let's say the protocol say, hey, I'm thinking of a number between 0 and 2 to the power of 50. Okay, this is a large number. So now the miner goes into this game, guessing until finally finds a number. Let's say that it took only 8 minutes for the miner to actually guess the right number and get the reward. Remember that the idea of Bitcoin is that blocks are mined roughly every 10 minutes. So in this case, the block was mined a little earlier than was expected. So what the protocol is going to do, the Bitcoin code, is just going to increase the difficulty. So next time around, they're going to say, you know what? I'm thinking of a number between 0 and 2 to the power of 70. So now you have even way bigger numbers, way more numbers to guess, which is going to push the miner harder to eventually guess it, but maybe it's going to take longer, maybe 12 minutes. So that's what I'm saying. It is not exactly every 10 minutes. It's somewhere close to it. So the protocol tries to adjust the difficulty to try to keep the block production every 10 minutes, just by choosing how big or how small the range of number to guess is going to be, or the difficulty of the proof of work. Again, this is oversimplified. We're going to keep digging into this later. Let me see if you have any questions so far. I think Truth has been answering those questions.
Yeah, no questions for now.
No questions for now. Some water break. All right. So as I mentioned, right, the protocol targets 10 minutes on average, but it's not exact number. It's just trying to adjust every time. Now, this guessing name, right, this solving the proof of work, what is called mining. And mining in 2011, at the early days of Bitcoin still, It was done with home computers, maybe with some special GPUs, but everything at home, right? But now, these days, 2025, mining has become so difficult, so challenging, because this difficulty adjustment keeps increasing and increasing. And the competition, because now you compete with multiple other parties trying to guess first this number or solve the proof of work first. Then now that trying to mine a Bitcoin requires pretty much a data center of only specialized machines that the only thing they do is try to guess the number. In this case, just to find a hash that matches. We're gonna go back to it later. The point here is that the complexity has increased incredible. This is why the energy consumption of Bitcoin is so high, because you need so much compute power to try to solve the proof of work and get rewarded with new BTC. So how much energy does the Bitcoin network consume overall? Well, it's kind of comparable to the consumption of Argentina or comparable to the consumption of Sweden, right? So whole countries consume almost as much as the Bitcoin network as a whole, which has been calculated to be roughly 0.55% of the global energy demand. Now, locally, the most of the sources for Bitcoin, at least that we know of, come from what's called like green energy, if you consider natural gas to be green. But a lot of that comes from renewable. And this is mostly because of price, right? Because one of the benefits of Bitcoin is that you can use energy. You can monetize energy close to the source, right? So you don't have to transport that in long distances. That's why you're able to take advantage of wind farms or bringing very close to hydro, or just create the dedicated power plants for it. Jakub is asking, is it guaranteed that every time a new block will be created, meaning that there will always be someone to solve the proof of work? Yes, there's always someone able to solve the proof of work. The only question is how long is that going to take to solve? That's the only question. Sometimes the difficulty adjustment is actually steep if there's a sudden change in processing power in the network, which has happened. Like, for example, the first time that China banned Bitcoin mining, there was a big drop on the difficulty adjustment just because a lot of computing power just went off the network and then relocated to different countries and the difficulty went up again. But yeah, there was always going to be someone solving the proof of work. Good question. Thank you. Okay, so I talk about proof of work a little bit, about energy consumption. Let's talk about another very crucial aspect of Bitcoin is how is your balance calculated? How do you know how much Bitcoin do you have in a network? So what's happening is that Bitcoin has a database that's called the UTXO database. And UTXO means unspent transaction. And in this database, it will say, for example, okay, let's say, talk about the Daniel's balance, right? Daniel has one UTXO of 10 BTC. So one unspent transaction that has one BTC. So if that is the only UTXO of Daniel, we know that his balance is 10 BTC. Easy. But it could be that you can have more than one UTXO in the database. You can have, for example, 3, like in the case of Jerome, right? So to know his balance, you can pretty much just add up all the unspent transactions that you have in this database. In this case, 2 plus 5 plus 0.5, 7.5 BTC. So this is the amount of Bitcoin that you are available to spend. That's why it's unspent transaction. It's Bitcoin that you can spend. Once you spend it, it's spent, and that is just removed from the network, it disappears. I mean, it is assigned to someone else as an unspent transaction, right? But the whole database is just a collection of amount of Bitcoin that you're available to use. How does Bitcoin solve double spending? This is a good question. I think you're going to get into the consensus protocol, right? Because double spending means that someone is creating a transaction that is spending the same. Let's say I have 10 Bitcoin, right? And I send 10 Bitcoin to Sutton, and I'm trying to cheat the system in sending the same 10 Bitcoin to Truth, right? That should not be possible, right? Because I only have 10 Bitcoin, I can just suddenly send to 2 different parties. So what's happening is that I am violating the rules of the Bitcoin protocol, right? So what happens is that every new block that is created, in this case, me as a miner trying to create a fraudulent block that spends the same thing twice, it's going to get detected by the other honest miners in the system. And because they're going to detect that I'm going to do something fraudulent, they're going to pretty much ignore my block and going to continue chugging along, ignoring my block. So I live in fantasy thinking that I was able to find, because this was called a fork. My Bitcoin is going to live in a fork that has no value. It is not connected to the main fork or the main trunk of the system that is actually recognized by everyone else. So that's basically how double spending is solved. Okay, so what happens when I send Bitcoin to someone? So let's say that Daniel is trying to send 1 Bitcoin to Maria, right? He's going to sign the message. Hey, it's me, Daniel. So he's going to give this note to the protocol, in case the Bitcoin protocol. And what's going to happen is that first the protocol is going to check that I actually have the funds, right? It's going to check all my UTXO to see if the addition of those UTXO actually is more than what I want to transfer to someone else. And then it's going to check actually the signature. It's like, is this actually Daniel signing this message, or is it someone else trying to pretend that it's Daniel, right? Because the protocol only wants to allow the owner of the Bitcoin to be able to move it, not someone else claiming to be this person. So if those two things are checked and are correct, like they pass the check, what is going to happen is that my initial UTXO that Daniel had of 10 BTC, what's going to happen is going to turn into 2 different UTXO. One assigned to Maria by 1 BTC, right? The one that I'm trying to send. And then it's going to get like the change back, right? The rest, 8.9 BTC, is going back as a different UTXO for Daniel. But you notice that there's 0.1 BTC missing this transaction. No, it's not 1 and 9. That is because you have to pay the miner to include your transaction in the block, right? So that becomes part of the miner UTXO. You're paying the miner to create this block that is going to create this transaction in the network. So just keep in mind that when you spend Bitcoin, you essentially create new UTXO, just send to the person, new UTXO, and then you get change back from your own UTXO, minus the fee that you had to pay the miner for being able to use the Bitcoin network. Let's go to another very important topic. What's a digital signature, right? And this is going to become relevant because if you remember the example we had before, Daniel was signing the message with his signature, right? But what is that signature in the concept of Bitcoin and cryptography? So that's what we're going to cover here. So it all starts with some interesting mathematics or cryptography called the elliptic curve cryptography, also known as ECC, right? So part of this cryptography, of this new math, there's implementation of this that is called the elliptic curve digital signature, or ECDSA, right? And in this system, what happens is that there's a private key and a public key, and those things are connected. You can derive the public key from the private key very easily, just using some cryptographic function. Now, doing the inverse operation, like trying to derive the private key or trying to guess the private key from just the public key, is deemed to be pretty much impossible, right? And that is the beautiful of the cryptography behind ECDSA. Now, when I say impossible, well, it is impossible for a classical computer, right? Computers that we use today. Even the most powerful supercomputer you can find today, is not possible to do this reverse operation. But it could be possible in the future for quantum computers, right? The algorithm for breaking this assumption is known, but we don't have yet powerful enough quantum computers to do this reliably, okay? So just keep that in mind, because a lot of the cryptography that underpins not only Bitcoin, but Ethereum, and a lot of our security online, like on the web, relies on this particular fact that it's impossible to guess the private key just from the public key, but that assumption is going to be broken at some point that might not be too distant in the future when the quantum computers become powerful enough, especially the error correction gets much better. Okay, so using ECDSA, how do you sign a message on Bitcoin? So what's going to happen is that every single person that uses Bitcoin is going to have its own private key that is unique. And what they do is that they take this private key and then they take a message. Could be just hello there, or could be just, hey, this is a transaction. You combine these two, and what you can do is that you can sign that message with your private key, and that's going to create in turn what's called a signed message, right? Which is going to look like gibberish to you and I, but you can use now this signed message, and then using your public key that is known to everyone, that's why it's public, you can verify very, very quickly that that message was actually signed with your private key without revealing that the private key itself, right? So it's a way to check, to authenticate you using your public key and never revealing the private key. It is a very reliable system and is used by many things, Bitcoin included, for this particular purpose, authentication. So how do you prove that you created a transaction on Bitcoin? So remember again, you ask the protocol, hey, send 1 BTC to Maria, it's me, Daniel. So first of all, you're gonna create the transaction that's saying, hey, send this amount from me to the sender, Maria, to the recipient, sorry. That's the message. And then you're gonna take your private key that is only known to you, and you're gonna sign that message, right? And that's gonna create a signature that is unique to your private key and to the message you're signing. Then you're gonna include your public key in the transaction itself as a new field, because it's visible to anyone, you can share it. And that's what then you're gonna give it to the Bitcoin protocol. And the Bitcoin protocol is gonna do that operation. That's gonna take the signature with your public key, and it's gonna say, oh, you know what? Yes, it's actually the private key of Daniel signed this message. So I know this message is coming from him. So I'm gonna allow this Bitcoin to move. So this is how the protocol verifies the sender actually controls the Bitcoin that it's trying to move. Halab is asking, one thing I still don't understand is how Bitcoin has monetary value when it's just internet money. That's a difficult question to answer. The easy way to answer that, there's a great book that I can recommend anyone, Bitcoin Standard. This is an amazing book that touches on that topic of what is money. And essentially, first of all, it's the hardness of the currency. It's the fact that you know exactly how much Bitcoin is going to be created and you know that it's going to cap at 21 million. That scarcity is very hard to enforce in any digital realm. And when you see, for example, in the physical world, you have a few things that are scarce like that, like, for example, gold. Like one of the cool things of gold is that, you know, it's not perishable, it lasts very long, but also it's fairly scarce. So that is part of the value. If gold were extremely easy to find, it wouldn't be as valuable as it is today, and maybe it would not be used as money as it was used in the past. So Bitcoin was the first digital asset that was able to enforce a level of scarcity that is actually stronger than gold itself. So that is part of the money, the value of money. But of course, it's part of the fact that it's a network effect. The fact that some people accept it as money and some other people as well, that start to create this ecosystem. But it's a good question, and there's a whole book just for that purpose. I recommend you to read it as well. Jeremy is asking, what are the incentives in long term for miners to participate in the network when reward is half to very little amounts? That is an excellent question, because the reward is decreasing every 4 years. So it means that the miner is getting less and less Bitcoin every time. But it's also true that as the halving continues, because less Bitcoin enters the system, it means that Bitcoin becomes like less scarce in the sense that there's less debasement or less inflation in the system, which makes the Bitcoin itself, the one that is already in circulation, more valuable. So a lot of the loss in the actual amount of quantity is offset by the value increase of Bitcoin itself, right? Because the miners care about the US dollar value of their reward. But no, at some point that is going to become a problem because that reward is going to become zero, right? So what is going to be the incentive for the miners? Well, incentive should be this fee that the miner charges for every single transaction they include in their block. The question is that in this one thing that Starling is trying to help to solve is that how do we increase the number of transactions in the network on Bitcoin so miners can get more from fees than from the subsidy? So that is the real difficulty trying to solve long-term for the health of Bitcoin. Good question. Thank you. I'm going to keep on going, but Truth, if you know the answer, please answer them. I just don't want to be too far behind here, but good questions. Okay, I was here, right? So we discussed how this signature is verified, how the protocol actually authenticates that someone is the owner of certain Bitcoin before sending. Okay, great. But now the question is, can you be hacked? Can this fact be exploited for someone to steal your Bitcoin, to pretend that it's you, to sign fake transactions? Well, let's see. Let's try. Let's say there's a hacker that's trying to create a fake transaction that is the same that the Daniel did before, right? Send what BTC from Daniel, but in this case, instead of Maria, send it to hacker, right? He's trying to steal the money. what's going to happen is that the hacker doesn't have Daniel's private key. It's going to have its own private key. So it can only sign this message with his private key, which creates a different signature, right? It doesn't matter if it also includes Daniel's private public key. The protocol is going to be able to know very easily that this signature doesn't correspond to the private key associated with this public key. That is one of the beauties of the cryptography of ECDSA, right? And this is done very easily, very quickly. So the protocol knows, you know what, whoever signed this message is clearly not the owner of this BTC because there's no match. It's this public key and the signature. So I'm not going to allow this transaction to go through. But what could happen is that a hacker could actually, if they manage to steal your private key, now they can actually do whatever they want. They're going to be able to send this message, send all the BTC from Daniel to the hacker, sign the message, and the protocol has no way of knowing that it's actually a hacker because it's going to say, well, this signature is actually, I can see that it's created by the same private key that this public key is derived from. So I'm going to allow this to go through. So your funds are going to be drained. So this is why it's so important to protect your private key. And your private key is encoding these 24 words, or is it 12? 12 or 24 words in Bitcoin, your seed phrase, because that seed phrase is essentially your private key, just encoded as words. So if someone else steals it, they can reconstruct your private key and now start to send transactions on your behalf and do whatever they want with your own Bitcoin. So always protect your private key. In your case, protect your seed phrase because that is your private key. Okay, we talk about ECDSAs, public key cryptography. Let's go to one of the great questions or big questions again. Why is Bitcoin considered to be a blockchain? Why do we use this term to describe Bitcoin? Well, I've been mentioning that what a miner does is to mine blocks, right? And this block basically has two big parts. It has a header and it has a body. So the body is going to include all the transactions that users creates to send Bitcoin to someone else. That a miner is going to say, okay, I'm going to include this transaction from people around the world. I'm going to put it in my block. And, I'm going to charge a fee for each transaction because it's part of the revenue model of the miner. All the fees that are being collected by the miner from the users are actually added to a single transaction at the top that's called the Coinbase transaction. That's basically how the miner pays itself to include these transactions in the block. And you can recognize this name, right? Coinbase. That's why this company Coinbase in the US chose that name, is the name of this transaction that pays the miners. So this is where the transaction fees are included, but also the block reward. This subsidy that we discussed before, all this is condensed in a single transaction that pays the miner money from subsidy and from fees collected of users. So that is the body of the block. Now in the header, you have multiple things. You have, for example, the solution or the proof of work challenge, like guess the number. You have the wallet address of the miner, like where to paste the money. That is called the Coinbase wallet. And then you have other fields more, right? For now, just focus on these two. It's good enough. We know that roughly every 10 minutes, a new block is mined because another miner solved the proof of work, blah, blah, blah. So that other block is going to have the same structure. Oops. But the one thing that's going to have as well, and that I didn't mention before, is that one of the properties in the header is a hash of the previous block, right? So it's going to be a reference in this block, a reference to the previous block. And then the block after that is going to have a reference to the previous block. And this back reference is what creates actually a chain of blocks or a blockchain. So the only block to not have a hash of a previous block is obviously the very first block in the system, the one created by Satoshi, the Genesis block. That's the only one that doesn't have this previous block hash. All the other blocks, they have it, and that's the chain that it gets created. So we talk about, okay, the hash of the previous block. What is a hash, right? We didn't discuss that. So let's take a look at that. So a hash is a function, like a programmatic function or a cryptographic function, where you give as an input any digital asset, like a PDF, for example, or a Google Doc. And it's going to give you a digital fingerprint, like a unique identifier for that asset, right? And you can pass anything to this hash function. You can pass an image, you can pass audio, you can pass video, anything that you represent as a digital format. You can give it to a hash function, and it's going to create a unique identifier, almost like a fingerprint, that is very different from any other file, right? So There's different hash functions that you can use. The one that Bitcoin uses is called SHA-256, and it's used for the proof of work challenge. So this hash creates a number that is between 0 and 2 to the power of 256. So this is a gigantic number. That's why we consider it to be a unique fingerprint, because there's so many combinations possible that it's extremely unlikely that two different assets will lead to the same fingerprint, the same hash. So to put this into context, this number is so large that it's actually larger than the number of all the atoms in the universe, right? This is one of the guarantees of randomness. Bitcoin uses a secondary hash function, we call it RIP-MD160, used for different purposes. This one is used for wallets. The hash is a bit smaller, to the power 160 maximum, but this number is still bigger than all the atoms in the universe. So there's a lot there as well as randomness. So SHA-256, RIP-MD160, this is the one that is used for most of Bitcoin. This is only used for wallets. So we're going to focus on the SHA-256. So I mentioned that the hash is like a very unique, no matter what the input is. And let me prove it to you. If I calculate the hash using SHA-256 of this string, just hello world, you get this number, right? Doesn't matter what number, just it's a large, very large number. If I only modify one thing, like an exclamation mark, not except this, it passes through the same hash function, I get a totally different hash number. So you see, there's no correlation. If you only look at the hash, you will never guess that the input is actually so similar. And that is one of the properties that creates this. It's impossible to guess what is the initial value from the hash. There's another property. It's very much impossible to guess that. Now, can we find the source of a hash, right? The same way that I mentioned that it's very hard to find the private key from a public key, although a quantum computer might, but classical computer is pretty much impossible. It's the same property for hashes. So going back to the same example of this hash of the hello world, we get this. Can we guess the opposite? If I give you a different hash, can you guess what is the initial value that created that? Well, no, because the computation will take longer than the age of the universe. And that is true even for quantum computers. Quantum computers will make that half the time. So it will actually speed up that, but still half the time of the age of the universe, that is not a feasible computation. So it is safe. It is safe even in the future of very powerful quantum computers. And that is a very important thing to keep in mind when we enter into validity proofs in ZK and zero knowledge, especially with ZK Starks, is that they use this property to be post-quantum secure. And that is the only validity proof that actually guarantees to be secure even in the face of powerful quantum computers. Because the only cryptographic primitive they use is hash functions. All the rest is just polynomials. Okay, so how does Bitcoin use SHA-256? I mentioned that it's used a lot in proof of work, but it's also used in different places. So let's go back to the block, right? Make sure that the block has a header and has a body. So the way that Bitcoin uses SHA-256 is that it's going to take all the transactions in the block, right, from the Coinbase to the user transactions, and it's going to pass it through this hash function two times, right? Like pass it once and the output pass it again from the hash, and that creates a digital fingerprint for all these transactions. They're all different, right? They just use the same icon for simplicity, but there are different fingerprints for each one of them. Now what they're going to do, next step, is just going to combine the fingerprint of two transactions. It's going to pretty much put them next to each other or concatenate them, and again pass it through this hash function two times. It creates another fingerprint of these two combined. And it does the same on the other branch. And then it repeats this process until you get to a single root hash, right? And that root hash creates a hash that identifies all the transactions that are considered to be at the bottom or the leaf. So this root hash is now included as part of the header, right? Say, okay, all the information that is contained in the block is identified by the root hash, right? Because the way it is constructed. This is called a Merkle tree. And the Merkle tree gets its name because you can think that the root hash is the root of the tree, these are the branches, and the actual values are the leaves of the tree. So important, Merkle Trees. That's another important property of Bitcoin. And we're going to see something very similar on Ethereum, but with a twist. All right, so how do we use Merkle Tree? So a very common way to use Merkle Tree is to check integrity. Let's say that we have a Merkle Tree created just in the right way, all the real transactions, and they lead to some root hash, that's fine. Let's say that now I try to create like a fake transaction. I try to include one, right? What's going to happen is that the first three branches are going to look exactly the same as the original one, but now we have a different fingerprint, right? Coming from the fake transaction. What's happening is that now this branch is going to be the same as before, right? These two are matching, they're exactly the same, fine. But now these two start to diverge because this is the concatenation of these two and this one is different. Now this hash is also different, right? One different here. And when you combine the two, now the root hash is completely different, right? So there's a root hash mismatch, and that's how you know someone is messing up with the information in the second Merkle tree. So Merkle tree, one property is that it's very easy to find when there's been a change in one of the leaves very quickly just by comparing the root hash. If they match, it is exactly the same information in the same order. That is something important. If something changes, even the order or the content, the root hash is not going to be mismatched, and you're going to see right away something's off. So that's one power of Merkle trees. How are Merkle trees also used on Bitcoin? Another nice property is that you can create a proof of inclusion. Basically, you can show to anyone that your transaction was included in a block using some properties of the Merkle tree. Let's say that you want to get a proof that your transaction was included in a block, right? And we know that each block will have its own Merkle tree, represents all the transactions in the block. So when you're going to ask the network, say, hey, give me please the fingerprint of the branches, of the other branches where my transaction is not part of in the block. Give me that as an information. And now I'm going to build the rest myself, just to corroborate that I'm going to get to the same root hash. So you do the dual hashing. Now you combine this fingerprint with the one given by the network, right? Then you combine that with the other hash given by the network, the other branch. And now you verify that when combining this, you get the same root hash in the block header. If those two things matches, now you know for sure that your transaction was included in the block. Without having to download the whole Merkle tree or the whole information and just do things step by step, you only need to process the branch that your transaction is on, and the rest information, the Merkle proof is given by the network. So this is a Merkle proof, and it's used by wallets, right? This is how a wallet can show you without certainty that your transaction was actually included in a block by a miner. Usually it's called a light client as well. Okay, so now that we know hashes, we can actually go back to the problem of what proof of work is in more detail, because it's not really just guess a number. It's a little more complex than that, and it's involved the use of hash function. So the Bitcoin miner says, basically, it tries to construct a block with all the transactions from users, and it says, I want to mine this block. What's the challenge, Mr. Protocol, right? It's going to ask Bitcoin. In Bitcoin, the challenge of the proof of work challenge is, okay, the hash of the header, so the information contained here, of your block should be less than a certain number, right? So you're going to hash this with the SHA-56, and whatever value you get, it needs to be less than a number I'm going to give you, or a difficulty I'm going to give you. So what the miner is going to do is say, okay, let me take the block header, and I pass it twice to the SHA function, and let's see what hash do I get. And I give that to the protocol. So is this the hash? Is this hash actually smaller? And the protocol said, well, no, this hash is actually not smaller than the one that they ask you. So try again. So the issue that you have is that if you keep always the same block header, if you don't change anything on the input of the hash function, you will always get the same output, the same fingerprint. So how are you going to be able to change the guessing here, trying to match to be smaller, right? If the block header doesn't change, the hash will always be the same. So something needs to change in the header so you can play with it until you find the solution that the protocol is challenging you to find. So how do you change the block hash? Easy. You add a new field to the block header that's called the nonce that you can set up the way you want, any number you want. So let's say you start with 0. It will give you certain block hash, right? Certain fingerprint. You will protocol say, is this smaller than what you asked me to do? People say no, try again. So what the miner does is just keeps changing the nonce, right, randomly, until it finally finds the right nonce that when hashed with the block header, it will give you a hash that is smaller than what the protocol is asking you. That is the challenge really of proof of work. So the key is the nonce, and that is part of the block header as well. So now that we have this information, we can revisit this blockchain. And we mentioned that, we have the Coinbase wallet, the root hash as part of the header. Now we know that we also have the nonce, and the nonce is the solution to the proof of work. And we also have a hash of the previous block. This is what creates the chain, this chain in the blockchain. So that is a much more accurate representation of what the blockchain, the Bitcoin blockchain is. Okay, so we know how these things are constructed. We know the root hash is constructed from a Merkle tree. The nonce is just try multiple different times till you find the right one. And this information about the miner itself, the wallet and the transaction. Another way to identify blocks is by height. And essentially it says, okay, the first block, the Genesis block, has height 0. The next one has height 1. So that's another value you're going to see attached to every block. What is the height? Basically, what is the number in the whole chain? Now let's go to the second biggest blockchain, Ethereum. And we cannot talk about Ethereum without talking about Vitalik Buterin. So Vitalik, he was born in Russia in the 90s, but actually moved to Canada with his family when he was just a kid. In 2011, he co-founded the Bitcoin magazine. So he started his career in this space as a technology writer, basically. But as a writer, he realized some of the limitations about Bitcoin. Not only him, and many people did, right? That's why for a time, there was a lot of different forks of Bitcoin doing slightly different things, right? And the main limitation is that adding new functionalities to the network require a hard fork. And a hard fork is basically you need to get consensus for everyone in the community to switch to a new version of the protocol that is different. This is a very messy process and hard to do, right? So it doesn't happen often. Actually, it hasn't happened at all. Only soft forks. Well, you can consider to be hard fork all the alternative Bitcoin, like Bitcoin Cash. You can think of that as a hard fork of Bitcoin as well. So in 2013, he actually proposed a new type of blockchain. And the main change is that this blockchain will be programmable without soft fork. So you can actually improve what it can do without getting into this, discussion of consensus with all the community all the time, which is super messy. And the idea is that this blockchain will work as a world computer that we can all use and we can all share. Back then, it was only an idea. There was no implementation. There was no code, but it actually had a name, Ethereum. There's a funny connection between Vitalik and the founder of Starkware, the creator of Starknet, Eli Ben-Sasson. The story is that when Vitalik was this writer, for Bitcoin magazine, he actually interviews Eli, mostly to know more about his work on zero knowledge. Because in 2013 also, Eli did a presentation about how to use zero knowledge proof for Bitcoin, for scaling, for security. So I think Vitalik was so impressed with the work that Eli was doing that when he actually invented and actually started with Ethereum, it was ready to, there was like a pre-sale of the ETH token before launching. Vitalik actually reached out to Eli to see if he wanted to invest. And to my surprise when I hear this the first time is that Eli rejected that, saying, I don't invest in things I don't fully understand. So of course, he always jokes that he regrets that decision every single day. But the funny thing is that when Eli launched Starkware, Vitalik was ready to jump in. So if you go to Starkware website, you can see that Vitalik is listed as an angel investor of Starkware, the company who later on created Starknet. And you can see it here. Right? You go to this website, you go at the very end, you see all the investors, and you can see that Vitalik is one of the angel investors of Starkware, along with Naval, which is another well-known person in the technology. So you see, Eli didn't see the promise, but Vitalik did saw the promise of Starknet and Starkware as a whole. So let's talk about back to Ethereum, the programmable computer. So, the limitation, as I mentioned, of Bitcoin is that there are some programs that run on Bitcoin itself, but these programs are defined directly in the protocol, right? And this is basically the programs that allow you to unlock your UTXO to be used in different ways, unlock with different methods. The issue is that to modify these programs or to add a new one requires a soft fork, which is this super messy process. Everything has to be agreed at the same time and just change the version of their code they're running. That's why it doesn't really change. It's always been fairly the same. It's very seldom changing. Now, the idea of Ethereum is that instead of the programs being embedded into the protocol, why did we create a protocol that you can put more programs on top on demand, right? So the protocol is just this computer that's able to execute any program that you want to deploy on top of. So that is the secret sauce of Ethereum. And these programs are written in a language called Solidity. It's not the only language, it's also Viper, but Solidity is the most popular one. And the idea that this programming language is custom made for the creation of a smart contract being a program that is supposed to be run only on a blockchain, in this case, only on Ethereum. So this way you can extend what Ethereum can do in infinite number of directions, because anyone can just create a new program and just deploy it, and now it's available for anyone else to run in this world computer that we will share. Now, the main difference between the code that you see on your IDE when you create the smart contract in Solidity versus the code that actually lives on the blockchain is that Solidity is a high-level language, right? It's very easy for a developer to use, but the code that actually gets deployed is using a very low-level language closer to machine code. It's called the EVM bytecode, okay? This is similar in the case of Bitcoin. Also, the programs that you see, they actually are in a very low-level language called the Bitcoin script. So you have a high-level language and low-level language. Bitcoin doesn't support high-level language, only low-level with Bitcoin script. Ethereum supports a high-level language in Solidity and Viper. Now, if you want different examples of other high-level programming languages, you have, as I mentioned, Solidity, Viper. Cairo on its target is also an example of high-level language. You have, of course, in the Web2 space, you have Rust, you have JavaScript, you have Python. Then low-level languages are not as common because as a programmer, you don't deal with them very often. Bitcoin script is one of those level language, the EVM bytecode as well. And then you have Cairo assembly, right? In the world of Starknet, when you compile Cairo, you compile it to Cairo assembly. That is the thing that actually gets executed on a Starknet. So that's one benefit, high level language that can be used to expand what a protocol can do. That is Ethereum. But now let's talk about how this world computer is used, because if it is a world computer, we only all share the same. How do we coordinate who's using it when, right? So Ethereum works, at least at a logical level, as a shared computer. That's why I put this image like a mainframe with multiple terminals, just because this was a similar idea. Back in the old days, they had this huge computer that will do all the computation, and the terminals was just a way to access the computer, so the computation happened here. Ethereum works logically in the same fashion, right? But instead of being one computer located in a central place, this computer is actually decentralized. It's running all over the world, controlled by many different people, and you can run your own version of the node as well at home today. But because it's logically one computer, you have to pay to run programs on this world computer, right? Now, the amount of money that you pay to use the world computer to execute some programs, it comprises on two different things. First of all, how complex is the computation you want to execute? This is the complexity of the transaction, for example. You can think of it of how many CPU cycles require or how many lines of code. But then it's also, and maybe more important, is how much storage you're trying to use in your program. So the more storage you want to use, the more expensive, and it actually increases very rapidly. It can get very expensive because the storage, the issue with storage is that once you put something on the blockchain in its storage, you're going to live there forever. Instead of a computation, you only do it once. I mean, whenever you run it, you finish the computation, it's done. It doesn't need to happen again. But the storage is going to remain always used forever by all the machines running Ethereum. That's why it's so expensive. Like, it's just to try to prevent the storage from blowing up too quickly. And this is why a lot of the NFT collections, they don't store the image on Ethereum because it's too expensive. They store it externally, and only some metadata is left on Ethereum itself. Now, the usage of this world computer is measured in something called gas. And the value of gas in dollar terms, like how much actually you pay in dollars, depends on what is the demand of the world computer. The more people are trying to use the world computer or Ethereum all at the same time, the more expensive this gas becomes in dollar terms. Because gas in itself is only a measure of utilization. It's not measured in dollar, but it has a market. There's an open market of how much dollar is a unit of gas. That is measured in Wei. Wei is like the smallest amount of Ethereum you can use. Which means that the more demand there is for Ethereum, the more expensive gas becomes in dollar terms, which means that the more expensive transactions become as well. And there has been some incredible spikes on Ethereum in the past where just a simple transaction will cost you $100. These days is actually pretty tame thanks to a lot of traffic moving to layer 2s like on the Starnet. But there was a time that it was actually pretty crazy. And you can track this. You can go to Ethereum gas. I always forget what is the name of the website. Gas tracker. Yeah, so this is basically the market of gas in dollar terms. They say that basically to execute a simple transaction, it will cost you 6 cents. It's extremely cheap these days. There was a time there was a lot of money. All right, back to this. But because, in Ethereum, you have this high-level language, Solidity, which is great for developers, great for programs, but it introduces one critical issue that actually all programming languages or high-level programming languages have, which is the halting problem. This problem was defined by Alan Turing, a very famous mathematician and mathematician, I think. There's a classification of programming language between Turing complete and non-Turing complete. And a Turing complete language essentially is a language that supports loops, like a for loop, like a while loop, okay? And if your language supports loops of any fashion, you run the risk that your program can run into an infinite loop. And it is pretty much impossible to tell by a compiler if a program can fall into an infinite loop before it gets executed. And of course, if you fall into an infinite loop on Ethereum, being logically a single world computer, you can essentially stop the world computer because it will get stuck executing one single transaction in an infinite loop and ignoring any other request. This fact could be used by hackers to create what's called a denial of service attack. So this is the reason why Satoshi was very smart to actually craft Bitcoin script as a non-Turing complete programming language on purpose. And it's very hard to create a programming language that is not Turing complete and is still useful. Bitcoin script is that. And that is on purpose to avoid this type of attack. Now, this makes Bitcoin script safer, but also less useful. Like trying to create anything with Bitcoin script is pretty difficult. Solidity, on the other hand, is a Turing complete programming language. So you have for loops, you have while loops. And because it runs on the blockchain, and the blockchain it runs as almost like a single thread global machine, it can cause the blockchain to halt if you manage to execute a program that falls into an infinite loop. So that's why Ethereum actually pioneered the notion of gas, just to mitigate this problem, the halting problem, or falling into an infinite loop and causing a denial of service. Mueller is asking, is it possible to invert the logic of the gas payment for instead of the transaction be paid by the user, it be paid by the contract itself? Okay. So what you're describing, it's not exactly what you're describing, but there's something called paymaster, which essentially allows a third party to pay for the gas of a user. And you can actually do that on a Starknet. It's not the contract paying for the gas, it's some other user paying for the gas. And you will do that, for example, if you want to create a protocol on a Starknet, like a Web3 app on a Starknet, for example, and you want to make it super simple for your users to not even think about gas, you can actually be the one paying for the gas of your users, right? It's not the smart contract, but it's a third party. So your user, for them, is just gas free. When you use the Bravos wallet on their mobile phone, you don't pay any gas. Not because it's free, it's because Bravos itself is paying for your gas under the hood using this paymaster approach. All right, measuring resources with gas. So I mentioned that you can compile Solidity to this low-level language called the EVM bytecode. So each one of these low-level instructions of the bytecode in Ethereum, they have a cost in gas. There's like a table saying, okay, this instruction is this amount of gas, this amount of gas. These values could change sometimes over time with discussions with the community, but there's a table with the cost of everything. So gas is a measure of resource utilization of Ethereum, either of computation or of storage. So a complex transaction uses more gas than a simple one, right? That's why a complex transaction is more expensive than a simple one to execute. But the important here is that each transaction must define a gas limit for its execution. So when you send a transaction to Ethereum, one of the fields that you include there, maybe you don't directly, but your wallet will include it, is what is the maximum amount of gas you're willing to pay for, right? Because you can also fall into an infinite loop by mistake or use more resources than you expect. In a transaction that you were expected to pay maybe $1, it could end up costing you, I don't know, $20, right? Just because it fell into this weird path of the execution. And you can stop that behavior, say, okay, I'm willing to pay maximum this amount of gas, or willing to use this maximum of gas. And if you get past that, I want this transaction to be stopped and not continue through and just being reverted. So that is the gas limit. So if the execution exceeds this gas limit, the transaction is aborted and reverted. Now, the protocol on its own also defines a maximum amount of gas you can use per transaction and also per block. This is to stop basically people trying to spam the network and falling into this infinite loop, but also creates a limit that there's a limitation of how much complexity you can include in your smart contract, right? Because it cannot go beyond what the protocol defines as the maximum of gas per transaction or per block. So this doesn't prevent infinite loops in theory, but it prevents denial of service attacks, because if eventually you're gonna hit a limit in gas, either defined by the user in gas limit in transaction or defined by the protocol in max gas per transaction and per block. So if something falls into this infinite loop, it will very soon stop and be reverted. So the computer is available to execute other transactions from different users. So no DOS attack. And every smart contract blockchain like Stargate uses this concept of gas for this same purpose. All right, there's another innovation coming from Ethereum that is connected to what we saw before. We talked about Merkle Trees in the past for Bitcoin, right? And we discussed that Merkle Trees were used mostly in blocks to define what is the root hash of all the transactions in the block, to check integrity, and also to check that your transaction was included in the block with a Merkle proof. Now, Ethereum builds on top of that to create a Merkel Patricia Trie. Question from Arya, but how can, show this answering, okay, good. So what is, okay, so Merkle trees are good for integrity check and for proof of inclusion, right? I mentioned that before, I showed you some slides, how it works. What Merkle trees are not good for is storage, because doing lookups on a Merkle tree is very slow, and they actually take a large size. If you want to store something very big with a Merkle tree, it actually takes a lot of size, because now you have to create all these intermediate steps, the intermediate branches with the hashes and the hashes and the hashes, all that aside from the actual data that you want to store in the Merkle tree. So it's not good for a big amount of storage, only small things like the transaction in a block. This is one reason why Ethereum and Bitcoin actually use a regular database, a key value database for storage, right? For storing like the UTXO set. It doesn't try to use Merkle trees for this purpose, because it knows that it's just so slow. So the question that Ethereum had, okay, how can we get the best properties of a Merkle trees, but also efficient storage, right? How do we get this idea of proof of inclusion and root hash, but also that we can use for storage, for example, all the global state of Ethereum instead of using a database? So Gavin Wood, he's listed as one of the main inventors of this variation of the Merkle tree called the Merkel Patricia Trie in 2014. Gavin Wood is one of the co-founders of Ethereum, probably the person with the most technical knowledge. They actually wrote, I think, the first client of Ethereum. He then went on to found Polkadot. So Merkel Patricia Tries expand of Merkle trees to be used as an alternative to a database. So you're going to have root hash, you're going to have storage proof, But then you're going to have also efficient storage and fast lockup, important things to be used as a database alternative. Now, Ethereum uses Merkel Patricia Tries to handle its global state and pretty much in any other place that Merkle Tree could be useful. Also, like for transactions in a block, also a Merkel Patricia Trie. It doesn't use Merkle Trees. So get ready. This is how a Merkel Patricia Tries actually work. It's a bit more complex than Merkle Tree. So let's go step by step. By the way, what I'm showing here, I just took it from a video, a YouTube video that's really good explaining how this works. I just turned it into a slide, but if you want to check the video, here's the link here. Let's first assume that we have 4 different wallets for, let's say, 4 different users. And I'm going to take a simplified version. Wallet addresses are long, like 20 characters, something like that, or 32, I don't know, long. I'm just taking a short one, 1, 2, 3, 4, 5, 6, 7 digits. These are in hexadecimal, so that's why you can see later sometimes. Let's say we have these 4 addresses and we want to store it. We want to store all the information in one Merkel Patricia Trie. What I want to store in this case is just the balance of each of these wallets, right? So how do we create this? The key here is to see, first of all, repetitions. In this example, all the wallets start with the same A7, okay? So in that case, you can start with what's called an extension node and say, okay, all of them start with the same A7. And then there's a reference to the next node. So the next node in this case has all the letters of hexadecimal from 0 to F. It's called the branch node. And then you start to branch out depending on what is the next value on the wallet address. For example, if you go for 1 that this one has, now you can go directly to a leaf node and just complete the sequence 1 3 3 5. So 1 3 I made a mistake here. So 1 3 5 5. Well, I can modify here, but you know what I mean. It's just a typo here for me. So now with this path, I've completed this whole address and I'm able to put the value. So in this path, there's 45 ETH, and this is the wallet A71135. I just made a mistake here. Then I can go to the next one, F, right? And I can see that F, the ending is 9365. So I put the key end, is a leaf node, and now I can just directly put the value. So there's 30 ETH in this value identified with A7F9365. What about the rest, right? And I have these 2 more to go through, but notice that they also have repetition, right? D3. So you can see that the Merkel Patricia Trie is very good at this compression, right? To try to find these duplicates and store it in a very efficient way. So I create another extension node, say, okay, whatever I've defined below this, they're going to have the same root, D3. So A77D3, A77D3. Sorry. You go to another branch node, and now you go to the 2 variants, right? So you go with 7, you get this address with 5 ETH, and you go with 8, and then you have 7. So basically, to reconstruct this wallet address will be A77D337, right? This one here. And this is how a Merkel Patricia Trie is created. And on top of that, each one of these nodes, either a leaf node, branch node, or extension node, they're going to have a hash associated with it. So you are able to recreate the idea of a root hash as well to check for integrity very easily. So there you have it, a Merkel Patricia Trie that can be used for storing almost like a database. And that's what Ethereum uses for the global state. Okay, now talk about the consensus and the execution layer. There's 2 layers on Ethereum with different purposes. So when you run a home node, this is what running an Ethereum node at home, a full node will look like. There's one version. That node creates this. You can build your own computer and just run the node as well, but this is a simple one. So this home computer will actually run 2 different, let's say, clients. One is the execution client and the consensus client, or layers. So the execution layer is the one that is dedicated to execute all the transactions in a block, is the one managing this global state with this gigantic Merkel Patricia Trie. And you have different clients that you can use. You can use Geth, you can use Nethermind, Besos, like different options you can use to run the execution layer. And then the consensus layer is the one that participates in the proof of stake, is the one tracking what is the chain head, like what is the latest value of the Ethereum blockchain. And you also have different clients that you can use. You can use Prism, Lighthouse, Teco, and other ones. This consensus layer tracks something called the beacon chain. Think of it like an extension of Ethereum for the consensus part. It's called the beacon chain, but it's just dedicated for consensus. Now, I mentioned proof of stake, right, for the consensus layer, but what is it? And how does it compare to proof of work? So in proof of stake on Ethereum, the idea is that if you will run your own node, right, in this case, it doesn't need to be a gigantic miner the size of a data center. It could be just something that run at home very, very easily. But you need to have at least 32 ETH, right, to deposit. And this is, at current price, is about $112,000. So it's a lot of money. Then you're going to deposit that Ethereum into a smart contract on Ethereum that's called the deposit contract. It's going to get locked there. So now, in that way, you are going to register yourself as a staker, right? So now you need to perform some operations on behalf of the network as a staker. One of those operations that once in a while, the network will ask you to propose or to create new blocks. This is similar to mining, right? But you're just assigned, it's your turn, create a block. But also to attest to blocks created by other stakers, okay? So you propose and you attest. And for each one of those operations, you get rewarded with new ETH, right? So similar idea to mining, the mining in a sense that you get rewarded for doing something, but without using the massive amount of computing power and energy. You mostly use economic incentives and you lock in money. Because the downside is that if your node goes offline, when it's your turn to propose a block or a test, you actually start losing some of this money that you put as a bond, the deposit contract. And the same will happen if you try to cheat. If you try to create a block that is some fake data or trying to do the double spend, you're going to get what's called slashed. Basically, the protocol is going to withdraw money from the bond that you put there. So that is your incentive to not cheat. You're going to lose your 32 ETH if you're cheating. If you're offline, you only lose a little bit every time the network's trying to ping you to try to do something. It's called leaking, I think it's called. But cheating is going to slash you very significantly. Now, if you want to become a staker, you have to do this investment plus running the node, and you'll get an annual yield of about 3 to 4%, which can be increased with something called MEV boost. This is beyond what I want to explain today, but it will get to 5 to 6%. So that's the reward for being a staker on the Bitcoin network. On Ethereum, and this is, in a nutshell, how proof of stake work, the incentives behind it. Last slide, a final comparison between Bitcoin and Ethereum. Very high level. So Bitcoin supports only one thing, sending BTC to one person and another. That's it. Ethereum supports the same with ETH. You can send Ethereum to different person, but also you can execute and deploy smart contracts so you can extend its functionality infinitely. The consensus and the way that it's secure in Bitcoin is proof of work. Guess this massive number with massive computing power and use a lot of energy. Ethereum is basically propose blocks, put a bond. If you cheat, you're gonna take your bond away. Bitcoin is not programmable, right? You don't have this high-level language you can compile and deploy, but Ethereum is. You can take Solidity, Viper, create your own smart contract and deploy it, and voila, you have something new on Ethereum ready to be used.